KTG, Kinetic Theory of Gases. Kinetic Theory of Gases? Yes, Kinetic Theory of Gases. Welcome my dear students. We are going to start a new chapter today, that is chapter 13, Kinetic Theory of Gases. In fact, in your textbook it is written only kinetic theory. But in this chapter the kinetic theory is explained of gases. So it is KTG. Let us see topic 13.1, that is the basic introduction of this chapter. Kinetic theory of gases explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms and molecules. Means the whole chapter is based on only one fact, that atoms and molecules are rapidly moving, especially in case of gases. Then topic 13.2, molecular nature of matter. See, atomic hypothesis. Atomic hypothesis says that all the things are made out of atom. See, this is a very fact that everything, whatever matter you take, solid, liquid, gas or even plasma, they are all made out of basically atoms, right? Atoms are little particles that move around in perpetual motion, that means continuous motion. Atoms are continuously moving everywhere, means whatever matter you take, atoms are moving. In solids, obviously this motion is constrained to vibrational motion mostly, but in liquid and gas, atoms are having all different type of motions. And these motions are perpetual motion, that means it is continuous motion. It is never stopping, it is never ending. Understood? The size of an atom is about an angstrom, that is 10 raised to minus 10 meter. So you can understand how small an atom is. In liquids and solids, atoms are spaced about 2 angstrom apart. Means the size of atom is 1 angstrom, but in solid and liquid they are 2 angstrom apart from each other. But in gases, the interatomic distance are in tens of angstrom. So in gases, the interatomic distance between atoms is quite large. It is of the order of some tens of angstrom. That means it can be 10 angstrom or 20 angstrom or 30 angstrom and so on. That type of large distance is there in case of gases. But in solid and liquid, the distance is nearly 2 angstrom or so on. As per Avogadro's law, equal volume of gases at equal temperature and pressure have same number of molecules. This Avogadro's law is very much important, particularly in this chapter. It says that if you take 2 vessels or 2 containers having same volume, and if you keep same temperature and if you keep same pressure as well, then whatever gases you have taken, the number of molecule inside this 2 container will be same. Suppose in one container you are taking nitrogen, in another container you are taking, let us say, carbon dioxide. But when the volume is same, temperature is same and pressure is same, you will find same number of molecules in both the containers, means the number of nitrogen molecules and the number of carbon dioxide molecule in both the container will be same. The average distance that a molecule travel without colliding is called as mean free path. Now this is an important definition, you have to remember, mean free path. See, in gases, as we have discussed, that all the molecules are having perpetual motion. So they are continuously moving. And when they are continuously moving, they are also colliding with each other. Now in such a situation, the average distance between 2 successive collisions of molecule is known as mean free path. Here we are taking average distance because it's very obvious that the distance between any 2 collision will not be same. Obviously, all the pairs of molecule will not have same distance between 2 successive collision. So we have to take an average value of it. So the average distance between 2 successive collision, or in other words we can say that the average distance that a molecule travel without colliding is called as mean free path. This mean free path is of the order of thousands of angstrom. Means it is very large compared to the size of molecules, compared to the size of atoms. The size of molecules or atom is just 1 angstrom, right? Whereas the mean free path is of the order of some 1000 angstroms. That means 10 raised to 3 angstroms. The gas appears to be static, but it is fully active. It has dynamic equilibrium inside it. See, in practice we feel like the gas is static, but at the molecular level it is fully active. Rather, it is very dynamic and it is having a dynamic equilibrium. In dynamic equilibrium, molecules collide and change their speeds, but the average properties of gas remain constant. See, this is a very important point, that in gas, molecules are colliding continuously and so their speed will be changing. But the average property of gas remains constant. Due to the collision and motion of the molecules, the overall property of gas doesn't change. It remains constant. That means, though the motion and collision will be taking place between molecules, the total pressure, temperature, volume of the gas will remain constant. It will not be changing. Now let us see topic 13.3, that is behavior of gases. Gases at high temperature and low pressure approximately satisfy the relation PV is equal to KT. Here P is pressure, V is volume and T is temperature in Kelvin. Mind well, this is very important, that here in this chapter everywhere you have to take the temperature in Kelvin. So T is temperature in Kelvin of the gas. Means it is found that if you take any gas at a high temperature and low pressure, then it will mostly follow this equation PV is equal to KT. Here K is a constant, but it varies with the volume of the gas. In fact, K is proportional to the number of molecules, capital N. Obviously, when we say that K varies with volume, that means K varies with the number of molecules. So K is proportional to number of molecules, capital N. So now we can write capital K is equal to NKB. Here this Kb is another constant and it is known as Boltzmann constant. The value of Boltzmann constant Kb is 1.38 into 10 raised to minus 23 joule per Kelvin. My dears, this you have to remember, that Kb is 1.38 into 10 raised to minus 23 joule per Kelvin. Kb remains constant for all different gases. So now from this equation K is equal to NKB, we can write the equation PV is equal to NKBT, and so we can write PV upon NT is equal to Kb, which is constant. Now let us discuss about Avogadro's hypothesis. As per Avogadro, the number of molecules in 22.4 liter of any gas is 6.02 into 10 raised to 23. It's a wonderful hypothesis, I would say, that for any gas, if the volume is 22.4 liter, then the number of molecules inside that gas will be 6.02 into 10 raised to 23 only. This number is also known as Avogadro number Na. So Na is 6.02 into 10 raised to 23. This amount of molecules are called 1 mole molecules. Means when the number of molecules are 6.02 into 10 raised to 23, then it is known as 1 mole molecules. So now mole number can be written as mu is equal to N upon Na. N is total number of molecules, whereas Na is Avogadro number. So this ratio gives you mole number. For example, if you are having total number of molecules, that is 18.06 into 10 raised to 23. I repeat, 18.06 into 10 raised to 23. Then 18.06 into 10 raised to 23 divided by 6.02 into 10 raised to 23 will give you 3. That means mole number is 3. Or say there are 3 mole of gas molecules. Alright. Now, the mass of 22.4 liter of any gas is equal to its molecular mass in grams. I repeat, if you take any gas that is having a volume of 22.4 liter, then the mass of this gas will be equal to its molecular mass. For example, the molecular mass of nitrogen is 14 gram, right? So when you take 22.4 liter of nitrogen, then its total mass will be equal to 14 gram, because 14 gram is its molecular mass. Thus, amount of molecules in a gas of mass equal to molecular mass is 1 mole. That means if you take a gas having mass equals to its molecular mass, then obviously the volume of that gas will be 22.4, and so the amount of molecules in that gas will be equal to 6.02 into 10 raised to 23, means it will be 1 mole. So we can say that the amount of molecules in gas which is having mass equal to the molecular mass is 1 mole, means it will be 6.02 into 10 raised to 23 in numbers. So obviously the ratio of total mass and molecular mass gives you mole number. So mole number mu is equal to m upon m0. Here m is total mass of gas and m0 is molecular mass of gas. Now with the use of these two equation of mole, that is mu is equal to n upon Na and mu is equal to m upon m0, we are going to derive some more equations. From equation 1 means PV is equal to n kBt, and equation 2 means mu is equal to n upon Na. We can write PV is equal to mu Na kBt. Try to understand this. At the place of capital N, we can write mu Na, and so it is PV is equal to mu Na kBt. But this Na into kB is equal to R. Mind well, Na is Avogadro number, kB is Boltzmann constant, and this R is known as universal gas constant. It is known as universal gas constant. So now this equation can be written as PV is equal to mu RT. This is perfect gas equation, or say ideal gas equation. Here R, which is a constant, is having a value 8.314 joule per mole per Kelvin, and it is known as universal gas constant. Now let us derive two more equations. From the equation PV is equal to n kBt, we can also write P is equal to n by V kBt. But n by V, that means number of molecules per unit volume, which is also known as number density small n. Small n is equal to number density. Look here, small n is number density. So the equation becomes now P is equal to n kBt. One more thing, from PV is equal to mu RT equation, we can write, see, mu is m upon m0 as per equation 3. So at the place of mu I am writing m upon m0, and so this equation becomes P is equal to m upon m0 RT upon V. But here m upon V can be written as density rho. So the equation becomes P is equal to density rho RT upon m0. Remember, this rho is mass density. And now we are going to see a very important phase of this topic, that is about ideal gas. A gas that satisfies the equation PV is equal to mu RT is known as ideal gas. So for ideal gas we can also write PV upon mu T is equal to R, and R is constant, so we can say PV upon mu T will be constant. In practice, no real gas is truly ideal. Listen these words. In practice, no real gas is truly an ideal gas. Still, at high temperature and low pressure, a real gas behaves nearly as an ideal gas. Now this is something what you have to remember, that at high temperature and low pressure a real gas behaves nearly to an ideal gas. Alright. Now this we are going to prove by the graph given here. See, this is a graph of PV upon mu T versus P. Look here, this axis is PV upon mu T and this axis is pressure P. Alright. Now as per this equation we can understand, for ideal gas PV upon mu T will be R and R is a constant. That means for ideal gas PV upon mu T versus P should come a straight horizontal line because it is constant. So we are getting a straight horizontal line for ideal gas. Now if for any real gas we can get this type of horizontal line, then we can say that real gas is also behaving as ideal gas. But see the tragedy here. Here there are three graphs of different temperature for real gas. Here T1 is the largest temperature and T3 is the smallest temperature. That means this curve is for the smallest temperature, whereas this curve is for the largest temperature. This shows that for any real gas, when the temperature is high, then the curve of that gas approaches towards the ideal gas. See, this curve is trying to be a straight line, means it is approaching to the line of ideal gas. As well as you can see this point. When the pressure is very low, at that time all the graph of real gas and ideal gas coincide on each other. That means at low pressure all the gases are behaving as ideal gas. So concludingly we can say that real gas approaches ideal gas at high temperature and low pressure. As I said that at high temperature and low pressure a real gas behaves nearly an ideal gas. Now here we will discuss Boyle's law and also prove that at high temperature and lower pressure the real gas obeys Boyle's law. Let us see. For ideal gas we know PV is equal to mu RT is the equation. Now if mu, that is the mole number, is constant and T, that is the temperature, is also constant, then obviously PV will be constant. Alright. So we can say P is inversely proportional to V. Pressure is inversely proportional to volume. Thus for ideal gas, keeping the temperature constant, pressure varies inversely with its volume. This is known as Boyle's law. Now here is a graph of P versus V, means it's a pressure versus volume graph. And you can notice that there are two types of curves. One is continuous curve which represents the real gas and another is dotted line curve which represents ideal gas. So in other sense we can say that the continuous line curves shows the practical graph of real gas and the dotted line curve shows the theoretical graph of ideal gas. You can also see that all the graphs are given for three temperature, T1, T2 and T3, where T1 is the largest temperature and T3 is the smallest temperature. For T3 temperature, the real gas graph is this one and the ideal gas graph is this one, where you can see that the real gas curve is quite different than the ideal gas curve at the same temperature T3. Now if you take T2, then also the real gas curve is very much different than the ideal gas curve at temperature T2. But when we see at temperature T1, the real gas curve is quite near to the ideal gas curve at temperature T1, right? That means when the temperature is high, the real gas curve is approaching the ideal gas curve. Not only that, if you take lower pressure, then look here. At this point if we say the pressure is very much low. So here in this region if we see, which is a very important region, both the curves are coinciding each other. That means at lower pressure, the real gas is approaching the ideal gas. So conclusively, we can say that at high temperature and low pressure, curves of real gas approaches the curves of ideal gas. Or we can also say that at high temperature and lower pressure, the real gas is also following Boyle's law. Now let us see here Charles' law. For ideal gas, we know that PV is equal to mu RT. Now here, if mu is constant and V is constant, that means mole number is constant and the volume is constant, then obviously we can write that P upon T will be constant. So we can also say that P is proportional to T. That means pressure is proportional to temperature. Thus, for ideal gas, keeping the volume constant, pressure varies proportional to its temperature, and this is known as Charles' law. When the pressure is proportional to temperature, it is obeying Charles' law. That is all for ideal gas. Now let us see whether the real gas is also following Charles' law or not. For that, look the graph given here. You can see this is T versus V graph, temperature versus volume graph. And here are different pressures. P1 is largest, then P2, then P3. P3 is the smallest pressure. Here also the continuous line curve represent real gas and the dotted line curves represent ideal gas. Here you can see that as the temperature is increasing, the real gas curve and the ideal gas curve are coinciding each other. You can see that the continuous line curve and the dotted line curves are coming close as the temperature is increasing. That means at higher temperature, the real gas is approaching the ideal gas. Moreover, for a given temperature, if we keep the pressure smaller, then the real gas curve is near to ideal gas curve. Let me show you that with this line. Here I have drawn a line at any temperature T. Let us say this is temperature T. Now, if I consider both the curves for real gas and ideal gas for pressure P3, which is the smallest pressure, then the distance between both the curves is this much. But if I take a higher pressure, let us say P2, then the distance between the curves of real gas and ideal gas is comparatively large. You can see this is the distance between real gas curve and ideal gas curve. Now, if we move further and consider the curves of pressure P1, which is rather incomplete. So first of all, I have to complete the curve. Here is the curve of P1. Okay. So now at pressure P1, which is the largest pressure, if we consider the curves of real gas and ideal gas, then they would coincide here and here. So the distance between the real gas curve and the ideal gas curve will be this much. So at a given temperature T, the distance between real gas curve and ideal gas curve is smallest in lower pressure, whereas it is increasing at higher pressure. So this again concludes that for given temperature at lower pressure, the real gas curve is approaching the ideal gas curve. So conclusively, we can say that at high temperature and low pressure, curves of real gas approaches the curve of ideal gas. That means at higher temperature and lower pressure, the real gas is following Charles' law. Now finally, let us see Dalton's law. It's basically Dalton's law for partial pressure. Let us see. Consider a mixture of non-interacting ideal gas at pressure P, volume V and temperature T. the mole number of each gas is mu1, mu2, mu3 up to mu n. So we are taking a mixture of different gases. All the gases are having different mole numbers like mu1, mu2, mu3 and so on, and the mixture is at pressure P, volume V and temperature T. So first of all we can apply ideal gas equation PV is equal to mu RT, where mu is total mole number. So obviously the total mole number mu will be equal to mu1 plus mu2 plus mu3 up to mu n. So we are getting PV is equal to mu1 plus mu2 plus mu3 up to RT. Now I can divide this equation by capital V and also can multiply this RT inside this bracket. So I will be getting P is equal to mu1 RT upon V plus mu2 RT upon V plus mu3 RT upon V and so on. Here this terms like mu1 RT upon V is like P1, mu2 RT upon V is like P2 and so on. These terms are known as partial pressure. These are partial pressure. Here P1, P2, P3 whatever you write are partial pressure. So now we can write the equation as P is equal to P1 plus P2 plus P3 up to Pn. Here P is the total pressure of the mixture, whereas P1, P2, P3 are the partial pressure of each gas, or we can say it is individual pressures of each gas in the mixture. Now what this equation suggests? It says the total pressure of the mixture of ideal gases is the sum of their partial pressures. This law is known as Dalton's law of partial pressure. So when we are taking a mixture of ideal gases, then the total pressure of the mixture will be equal to the sum of all the partial pressures of all the gases. That is known as Dalton's law of partial pressure. Alright. So here with students, I complete this lecture here, and as I always tell you, the same thing I would like to repeat, that all the equations which are given in bracket are important. You have to remember it and you have to note it down in some other notebook. And also I would add that the PDF of this writing work has been prepared and the link of that PDF is given in the description box. You can download that PDF and can write the whole lecture from that PDF. Alright. So herewith signing off, Anshul Baldania. Take care.